Hi everyone, and welcome to our second lecture video today, all about different states of matter, solids, liquids, and gases. By the end of this lecture video, you will be able to compare and contrast the movement of solids, liquids, and gases at the molecular level and summarize properties of gases. This is going to set us up really nicely for the next chunk of our unit, all about gases. So we have to talk about the movement of all of these states of matter, the way they are shaped, their volume, and their densities. So we're going to break down this table here row by row. We spent all of our last lecture video talking about solids. As a reminder, solids are relatively dense. We can look over here and over here, that they're relatively dense because our molecules or atoms or particles are really compact. They're densely packed into each other. So they have a high density, and ultimately that gives a really defined volume and shape. If we look over here, we ultimately see that this crystalline solid has a really defined volume and shape. It has a shape of a cube, and it has a very specific volume. That's characteristic of solids. And in terms of their molecular motion, like what we talked about in the last lecture video, they are able to vibrate and rotate around themselves in kind of fixed positions. They bounce off each other back and forth, and they vibrate as well. As a reminder, all states of matter have movement of their particles. Nothing is ever going to be completely at rest. The next state of matter is a liquid. A liquid, which is shown here in this animation and over here in this center Erlenmeyer flask, has a relatively high density too. We're able to explain that it has a relatively high density, not as high of a density as a solid, but generally high. We're able to explain this because the particles that are shown down here are really compact with each other, which means that they have a relatively high density. In terms of their volume, they have a well-defined volume, but the shape can change easily. I have a water bottle right here, which we can say is half filled with water. That amount of water has a very defined volume. If I have 100 milliliters of water, that's a very defined volume. But if I put that 100 milliliters in this container versus my coffee cup container, these are different shapes. So ultimately, a liquid takes the volume of a liquid takes the shape of the container it is in. We see that over here as well. We see that our liquid particles are relatively compact, so they have a high density, and they have a defined volume, but they're occupying the shape of the Erlenmeyer flask. And thinking about how our liquid particles move, they vibrate and rotate like the solids, but they have more space to move around. These positions of our different particles change from time to time. We see here that our particles are mixing around. They're able to move around each other. Overall, our liquids have a lot more movement than our solids do because our solids are really compact, and our liquids, while they're still dense, aren't as dense as our solids are. We have gases as well, and gases have a relatively low density. That means they're not compact together. If we look at this flask down here, we see that our six different particles shown in here aren't compact together. They take up the entire container. So they have a relatively low density. They occupy the shape, they occupy the volume of any given shape. So we would say here that the volume of our gas is equal to the volume of this flask. We would then be able to say by proxy that the shape of this gas is occupied by the shape of that flask as well. And if we look at this animation here, we start to see some different characteristics of gases, which is why we spend a lot more time eventually talking about them. Gases move around their entire available volume. They're going to keep moving around each other, and they're going to keep moving around and bouncing off of each other and bouncing off of the walls of their container. And that's going to guide us into some special properties of gases as well. The last state of matter, which we don't focus on too much in chemistry, is plasma. Plasma has a low density and it takes different shapes, does not have a defined volume. And in terms of plasma, if you've ever seen a video of a grape inside a microwave, it starts to like light up and looks like it sparks. That's generating plasma. And this is ultimately due to random motion of ions and electrons throughout an entire available volume. The three primary states of matter that we're going to spend a lot more time talking about are these first three, but it's important to know that plasma is a state of matter and it still exists. To wrap up this lecture video, let's talk a little bit about some special gas properties that set them apart from solids and liquids. Solids and liquids are incompressible versus gases that are compressible. Here in this video, it's showing gas molecules or gaseous particles being decompressed. This piston right here, if I push it down, it ultimately compresses the gas molecules, which makes them not able to move around as much space. I cannot do the same thing with solids and liquids. And because they're compressible, that's going to guide us into some special properties that we'll talk about in the next couple of subunits. And because of the spacing of particles between a gas, the intermolecular forces have a minimal impact. If we go back to our animation of gas molecules moving around, we notice that they're really not close to each other. At no point do any of these particles collide or interact because they have so much space to move around in. Ultimately, that means that they don't really exhibit intermolecular forces on each other because they don't get close enough to each other. And lastly, something that is analogous to what we've seen in our previous lecture video, if I increase the temperature of my system, ultimately that gives my particles thermal energy, which means that they have a higher kinetic energy as well. If they have a higher thermal energy or higher kinetic energy, this ultimately increases the spacing, which allows them to overcome intermolecular attractions. The higher temperature, the more energy, and the more energy means we're starting to break those intermolecular forces. Recall from the previous lecture video, if that's a little bit confusing, that important slide where I talked about melting and how we can understand temperature in relation to intermolecular forces. That's it for this lecture video. Stay tuned for our next class, starting to talk a lot more in depth about gases. Bye, everyone.